Good afternoon, HVAC team. So for mile 130, we're going to be moving on to chapter 32. So let me go ahead and get started on that. So chapter 32 is alternating current fundamentals. The objectives are identify the different types and categories of electricity and electrical power systems used in the HVAC industry, explain the basis for magnetic induction in coils and transformers, explain how capacitors work in AC circuits, discuss the uses of single-phase and three-phase power, describe how electrical power is generated, state the importance of overcurrent protection. So, types of power sources. There are two common types of power, direct current and alternating current. Double check one thing. So DC power can also be used for control systems and on solid state modules for defrost and overcurrent protection. For these applications, the DC power is often converted from AC power through a rectifier instead of using batteries. So types of power sources: invisible magnetic field lines, like poles repel each other and opposite poles attract. So I'm sure you heard that before, so let's get into how that works. A force called a magnetic field transmits outward in all directions from magnetic materials. The invisible lines of force are referred to as magnetic flux and are shown radiating from the magnet in figure 34.1. Lines of force are always considered to leave the North Pole and enter the South Pole of a magnet in continuous loops. Like poles repel each other and opposites attract. So it's that loop that's causing the like poles to repel and for the opposites to attract. So basically, if the magnetic force is leaving from the North Pole and then coming in the South, if you were to have another North facing directly into this one, they're both going to be forcing the magnetic field outward and then going into the South. So if you put two Norths together, they're going to repel. But if you put a North by the South is where it goes in, the North is where it comes out, so they're going to attract. Electromagnetism and induced voltage. So when current passes through a conductor, a magnetic field is produced. The magnetic field has no poles, but similar to magnets, there is a continuous loop with a specific direction. The left-hand rule is used to determine the direction of rotation of the flux around the conductor. Imagine holding the conductor held in your left hand with your thumb pointing in the direction of the current. Your fingers will align in the direction of the flux. Electromagnetism and induced voltage. So there's another phenomenon that is exhibited with conductors. If the conductor is moved through a magnetic field, a voltage is induced in the conductor. So these conductors that are going through, so here's a conductor, you got four of them, but there's no current in these two because they are not in the magnetic field. But these two that are in the magnetic field have induced current going through them. So magnetic induction in coils and transformers. So when the wire is coiled with a weak magnetic field around each section of wire, combines to form a stronger magnetic field around the coil. So the more turns you have on that coil, the stronger the magnetic field is going to be. The addition of an iron core to the coil concentrates the magnetic lines of force. So this coil, well, this one doesn't have the core, but this one does. And that's how transformers work, actually. So I got a transformer here, but this one, I guess this one wouldn't be the best example because it's covered, but there's two coils inside of here. There's a secondary and a primary, and they're inside of this this transformer, and they wrap around this iron core. And the one with the more turns has a larger or a stronger magnetic field than the one with the less turns, and or the less, you know, the less amount of wire coiled up around that core. And the one that has the more coils or the more turns on the coil is the primary, and it has a higher voltage than the secondary because the secondary has less turns on the coil. Solenoid valves, a typical coil that would be used for a solenoid valve. Solenoid valves are electrically operated valves that open and close automatically by energizing or de-energizing a coil of wire. So once there's power going into this wire here, the magnetic field is going to be generated inside of here, and it's going to cause what the contact, it's going to cause the valve that is connected to open or close based on that magnetic action. So here we go. So this is a solenoid valve. So when there's power to the, so this one's closed. There's no power going to it. So that blue one would be your hot, and then white, off-white, grayish, whatever, that gray one will be your neutral. So the power coming in is going to energize this coil. It's going to create a magnetic field. And once that happens, this plunger is going to be, so once this magnetic field is created, this plunger is going to lift up because of the magnetic field. It's going to pull it up, and it's going to allow for fluid to flow through this orifice. So right now, nothing is flowing through here because this plunger is pushed down on top of it. So on this one, you can see the current coming through here. You can see your magnetic field on that coil. And then all of a sudden, now this plunger is being pulled up by that magnetic force, and it's allowing the fluid to flow through this orifice now. So that's what the solenoid valve, or the coil of the solenoid valve, does. It, once energized, it generates a magnetic field that will pull, that'll move a mechanism. In this case, it's going to move this plunger up and then allow the fluid to flow through the orifice. Relays, contactors, and transformers. So when current flows through the coil, the iron core is magnetized and is drawn into the coil. This raises the iron core and changes the position of the contact relays. Of the relay contacts. Transformers contain a single iron core that is wrapped with two separate coiled conductors known as primary and secondary. So that's pretty much kind of what I was showing you on the transformer. It's hard to see, but inside of there, there's two coils that wrap around. This side is the secondary, and then this side is the primary. And it's just coil of small copper wire that just wraps around it. On your contactor, there's also a coil. This one is also covered. I wonder if I can peel this off. It's kind of in there. I should have probably did this beforehand. So underneath this plastic insulation is a coil. This white part right here, that's just insulation. Underneath that is the copper coil. I really want to pull that off now. I'm gonna have to do another video. But anyways, there's copper right here. That's the coil. And once that coil is energized with your 24 volts coming in from your board, you're gonna have your 24 volt signal here. You're gonna have your common wire here. This is your coil. These two are connected directly to this coil here. It's soldered to that copper wire. So once this coil is energized, it's going to generate a magnetic field. That magnetic field is then going to pull the contacts shut. So we all kind of know how that works. I mean, this is probably just review for most of you. Well, actually, no, because this is my 130 class. So no, this is probably your first time. So whether this is review or your first time, that's how the contactor works. So it's similar to this graphic here. So you got the power coming in, it's going to create a magnetic field, and then this is going to get sucked up, and then this open contact will then become closed. Right now, this one is de-energized. This is the same graphic, but energized. So now you can see the lines indicating your magnetic field. This contact has been pulled up because of that magnetic force, and these contacts are now closed, making contact because of the magnetic field. So open contacts, closed contacts. And that magnetic field is generated because of the current. So once there's current applied to this coil, the magnetic field will be created, and then the contacts inside of here. So I don't know how well you can see that, but those brass contacts here, here, and here are not actually making contact with the surface below them until this coil is energized, and then it becomes pulled in. So that is how the contactor works. So if you got 120 volts here, just waiting to go through to the other side and then power up your motor or whatever's on the other side of this, your compressor, your condenser fan motor, that's not going to happen until this pulls in. So if you got 120 volts here or 240 volts right here, this is going to sit there waiting all day. If you check your power up here, it's going to be nothing. If you check here, you're going to have 240 just waiting to go. And it won't go until you have your 24 volts applied to your coil, and then it's going to pull that contact down, and it allows the 240 volts here to now pass to the other side and energize your motors and operate your motors. So that is how the magnetism comes into play with our contactors. And relays work the exact same way. They look different, but there's contacts on the inside, and they change position once the coil is energized. So you have certain contacts that are normally closed or others that are normally open. And whichever the case, once that coil is energized, it's going to change the position of those contacts. And it's going to turn something on or turn something off, or do both simultaneously, turn one thing off and turn another thing on when you're dealing with your relays. So here's your transformer. So there are two types of transformers: step down transformers and step up transformers. Step down transformers are often used to reduce line voltage required for motor starters to lower voltage for the controls. The amount of voltage induced in the secondary winding depends on the ratio of the number of turns in the primary winding and the number of turns in the secondary winding. So again, so this being your transformer, your primary side has 4 turns on it, and it's generating 1 volt. And then on your secondary side, if you had 1 turn, you'd be generating 0.25 volts. Or if, let's say, you had 2 turns, then you'd be generating 0.5 or half a volt. So that's how it works, because because inductance, because remember, the magnetic field is created by the coil being wrapped around it, and that conductor going through the coil is going to induce a certain amount of voltage, and that's going to be determined by how much of a magnetic field you have. 4 turns over here, more magnetic field. 1 turn over here, less. So you got 0.25 volts over here as opposed to 1 volt on the primary side. Magnetic induction in generators and motors. So figure 3417 shows current being generated through a single loop of wire rotating in a fixed magnetic field. As the loop turns clockwise through the magnetic field, a flow of electrons is established in the wire. AC motors and single-phase voltage. This induction principle is also applied to the construction of AC motors. The basic motor has 2 coils wrapped around stationary cores called stator poles. As AC current flows through the coils, the stator poles are magnetized. The stator field induces an opposing field in the rotor, and the principle of attraction and repulsion causes the motor to run. Figure 3419 is a diagram of a single cycle that is repeated 60 times per second, or 60 hertz, on a continuous basis. This is called single phase voltage. And single phase power is commonly used for residential and small commercial systems. For larger motors, generally 5 horsepower and above, 3-phase power is normally used. This requires an additional, this requires the addition of one more conductor in the generator. So let me just back up. So right where it says the principle of attraction and repulsion causes the motor to run, there's kind of a little graphic here that shows that. So you have your south poles here and your north poles on the opposite side. So this north is gonna be attracted to the south here, but then the south over here is gonna be attracted to the north over here, and that's what's gonna kind of make this thing want to keep spinning. And so the same thing is happening over here on 3-phase, but you just have more an additional conductor. All right, so resistive and inductive circuits. A resistive circuit contains at least one resistive load, such as an electric heater or lamp. In the inductive circuit, the current lags or is out of phase with the voltage. So you can kind of see the lag here between the voltage and the current on the inductive circuit. And this symbol here is your capacitor symbol. You're going to see that on your meters. This is the function that you want to put your meter on when you're checking your capacitor. So capacitors are broadly categorized as either polarized or non-polarized and variable. With variable capacitors, the curved line identifies the plate that is electrically connected to the frame or adjusting mechanism. The rolled foil types, with rolled foil types, the curved line represents the outside foil, and the load connection on the capacitor is identified by the color band at the end. Electrolytic polarized capacitors will have markings to indicate polarity. So these capacitors are a little bit less common in what we do. Let me just grab one that I have. So this is the typical run capacitor that you'll see in an AC system. And this one happens to be a bad one. I could tell by looking at it, because if you look closely, this top surface is convexed. It's kind of bubbled out. So when you see that, you know that it's a bad capacitor. Sometimes it'll be bubbled out at the bottom too, and if you try to sit it upright on the table, it'll rock. This one, I don't have my meter with me, but if I were to check it right now, I'm pretty certain it'd be a bad one, because you can tell right off the bat it's a dead giveaway when it's bubbled up at the top. So this is supposed to be a 7.5 microfarad capacitor. Guarantee you we're not getting 7.5 out of this one. Moving on. Capacitors and AC circuits. A capacitor is usually connected in series with the load. Obviously, no current can flow through the capacitor because of the dielectric, which is like an insulator. Initially, the current does flow through the series circuit. When the switch is closed, the supply voltage is applied across the capacitor. Following the initial rapid flow of electrons, the rate of current flow reduces, as shown in the downward movement of the current waveform. As electrons leave one plate and accumulate on the other, a potential difference begins to develop across the capacitor. This difference is created by current flow and therefore lags the current. In this circuit, which contains a resistive load, current leads the voltage by 45 degrees. Electric services. Electric utility companies use transformers to produce this service. So outside your house on the power, on the pole somewhere on the power lines, you'll see these big trash can looking things. I used to wonder what they were as a kid, but so those are giant transformers to those that don't know. So on this one, for example, you have 4,800 volts coming in, and then so they're coming in through these lines, 4,800 volts, and then the transformer steps it down and it's coming out at 240 volts. So this 240 is then fed to your electrical panel for your house. So all your appliances and everything runs off of 120, but if you happen to have an AC unit, then that will be 240, and the difference will just be a single pole breaker for your 120 volt circuits versus a 2-pole breaker for your 240 circuit for your air conditioner. So your panels, your residential electrical panels are 240 volt panels, and that is coming straight from the transformer right here, which gets its power straight from Edison. And then over here, you got a similar setup. This one, you got 2,400 volts coming in and 240 coming out, and then that 240 again is fed to your breaker panel. And that is an electrical symbol. I'm gonna zoom in on it. This is an electrical symbol you need to get familiar with as well. So 240 volts and 120 volts, all these other markings, if that wasn't there and you just saw this little squiggly next to this little squiggly with the lines in the middle, that is your transformer symbol. So just get used to that symbol. You're gonna see it a lot on every diagram where a transformer is used, which it always is. Let me break that down really quick too. So the transformer in that example is taking the high voltage from Edison, breaking it down to something to what's useful for us with our appliances, because our TVs don't need 4,800 volts. But where does that come into play in air conditioning? So every system has a transformer. You got a lot of things being using power in your system. So let's take your 3 motors, for example. You got your blower motor or your circulator motor, whichever one you want to call it, your indoor motor, the one that provides the air. When you put your hand in front of the vent and you feel airflow, that's because of your blower motor's turning. That's a 120 volt motor. Then you have your condenser fan motor outside by your compressor, and then the compressor itself is a motor. Those are high voltage motors. Those run off of 240. Then even if it's gas heat, then you got a 4th motor. You got your induced draft motor, which is in your furnace, also is a 120 volt motor. But then you got your thermostat that controls it all. Now your thermostat doesn't need 120 volts to move to open and close tiny little circuits on the little circuit board that's on there, because your thermostat basically is a circuit board. When you call for cooling, certain contacts need to be closed, certain things need to be open. We need to energize certain things. When you call for heat, you need to energize different things. The circuit board on the thermostat is doing all that. It's communicating, saying, okay, we need the heat, so okay, we're gonna need our induced draft motor, we're gonna need our high surface igniter, we're gonna need our blower motor, we're gonna need our gas valve. We need to power those things. So the thermostat is what's communicating with the system and sending power to those specific items. Oh, okay, let's switch the thermostat to cooling. All right, well, now we need our compressor to come on. We need our condenser fan to come on. We need our blower motor to come on. We don't need the gas valve, and we don't need the induced draft motor, because we're doing AC now. So the thermostat is sending the signals telling these things to come on. It's doing that with 24 volts because all it's doing is opening and closing contacts. So that 24 volts, where does that come from? We have a 120 volt system. Where are we getting these? What's powering all this 24 volt stuff? Well, that's where your transformer comes into play. So your primary side, which is this side, you're getting your 120 that's that's coming into your unit to power up your unit, you're going to take that same 120 and you're going to step it down to 24 volts. So all your relay coils and contactor coils are all going to get its 24 volts straight out of the secondary side of your transformer. Because and that's what's called your control voltage. You have your operating voltage, which is 120 or 240, depending on what motor's being operated, because that's what it takes to turn that motor. But then you also have your control voltage, which is which is 24 volts. And that 24 volt signal is coming from the thermostat to the board, from the board to your contactor coil. And again, once that 24 volts comes from your board to your contactor coil, boom, it closes the contacts, and now it allows your operating voltage to flow from here to here and bring your motors on. So there's two. There's your primary voltage or your operating voltage, which is going to be here and here, but then there's also your control voltage, which is here on the coil, because you need 240 to bring your compressor on. That 240 is right here just waiting to go, coming from your breaker panel. Just sitting here waiting to go. And not until your 24 volts is energized or energizes your coil saying, hey, we want the AC on, go ahead and close this. The 24 volts closes this, the 240 actually runs the condenser. So operating voltage, control voltage. So you have both, and that's the whole point of having your transformer in your system. That's where your low voltage is coming from. All right, three-phase 60 hertz delta system. The three-phase systems are commonly used for sizable commercial and industrial application or installations. These transformers have 3 hot legs of power and 1 neutral leg. This type of power supply is obtained from a delta transformer secondary hookup. Three-phase systems are commonly used for, nope, same one. All right, then the 208 volt / 120 volt three-phase 4-wire Y-connected system has generally superseded in large buildings by the 480 volt / 277 volt three-phase 4-wire Y-connected system. So basically the 208 120 has been pretty much replaced by the 480 277 three-phase transformers. .480 volt system. So this is pretty much the hookup. I mean, you got your 3 phases and then you have your neutral leg. So in summary, alternating current is the most common source of power used for HVAC systems. The typical frequency is 60 hertz. 2 important characteristics of AC power include phase shift and impedance. Power distribution systems can be single or 3-phase. Single-phase power is typically used for most HVAC residential and light commercial systems. 3-phase power is more commonly used on commercial applications, the bigger stuff, 5 horsepower and up motors and so forth. So anyways, that is all for Unit 15. The rest will be in your book. Definitely read the chapters. Always read your chapters before doing your review questions, which are on FlexiQuiz now, by the way. So go ahead and study up and stay safe, stay healthy, and I will see y'all on the next one.